Hi everyone, this is another training video on simulation of processes in avionics. First of all, I'd like to take you back a little bit to practical 2. Now let's take a look at what we've got here. So far, we tried to use the system of basis functions created before this system of power functions. We looked at these functions. Now we'd like to find a decomposition of, for example, this cosine function on the interval from 0 to 1. We decompose this x using these basis functions, system of these basis functions. Now, how do we do this? Actually, formally, from the mathematical standpoint, it looks like this. We find a decomposition in form of polynomial, where xa is actually a decomposition, a representation of this signal x using a system of basis functions s. Now, basis functions, they're included into this polynomial. X capitals from k here are the coefficients of these terms in the polynomial. K runs from 0 to n. K runs from 0 to 4. N equals to 4 in our case. So basically, to find a decomposition of signal x from t, which is equal to cosine pi times t to raised to the second power, we need to find some coefficients. These coefficients can be found formally by minimizing the error of decomposition of signal representation using basis functions. So x sub a from t is the signal representation using this basis function xss. X from t is our initial signal. So beta from t is our error. Minimizing error gives us this mathematical formula, where x with a bar on top, x bar, equals to w 2 minus 1 times q capital. These are two matrices. Actually, this is the matrix and this is the vector. Formally speaking, that's a very simple representation. So x, all these x's, you can see that it's not a single x, right? It's a system. It's actually a vector of x's with k running from 0 to 4. Actually, we have five functions here. We have t raised to the 0th power, which is constant. We have t raised to the first power, which is linearly increasing function. T raised to the second power, which is parabolic function, and so forth. So, formally speaking, we've got this formula where W is the matrix, inverse matrix, which coefficients can be found formally from this equation. Q is another vector, which coefficients may be found from this formula. Again, we have lots of indices. We have I, j running from 1 to n plus 1. Actually, if n equals to 4, it means that this I and j run from 1 to 5. We have 5 functions. So as we multiply, so let's look at this formula. Every coefficient of this particular matrix, W sub I j, equals to the integral over the interval from 0 to 1, which is our 0 to t capital. R from t is some weighting function. We can disregard it or assume it a constant. So we can disregard this for a moment. Let's look at what we've got inside. s sub I minus 1, so times s sub j minus 1. So these are just the indices. So with index I and j, so it means, for example, we have the first coefficient, the w1, 1. So we need to multiply s0 times s0. So we multiply the first function, t raised to the 0th power, times t raised to the 0th power. So we multiply the same functions. When these indices are different, then we multiply s sub 1, for example, times s sub 2 or s sub 3 and so forth. So basically we need to multiply all these functions on all these functions. So basically we need to form a matrix where we multiply these whole functions. So the diagonal elements of this matrix W will be represented by these functions multiplied by themselves. For example, the W1, 1, W sub 1, 1 will be equal to multiplying S0 times S0. W1, 2 will correspond to multiplying S0 times S sub 1 and so forth. So formally we can multiply this whole matrix or vector, we can by another vector which will be transposed. Okay. So formally, by multiplying this system of basis functions by themselves, we generate a matrix. Let's look at these Q's, Q capitals with a bar on top. Again, we disregard this weighting function and we multiply our basis function with a subscript I minus 1 times x, where x is our initial signal. In our case, it's cosine of pi times 2 raised to the second power. So w's represent these basis functions multiplied by themselves. Q's represent these basis functions multiplied by the signal. And we need to integrate these products. So formally, this is it. Maybe not very simple, but nothing complicated so far. The thing is, sometimes we use these functions, like in this case, which are not orthogonal. So this means that if we multiply these these basis functions with different index, we are getting, and after integrating, we're getting non-zero value. So this complicates things a little bit, but for Matlab there is nothing impossible. So we just proceed creating a formal system in Matlab for obtaining these coefficients, these W's, the elements of the matrix, these Q's, elements of the vector, to find this vector of coefficients representing the decomposition of our signal onto the basis functions S from T's. So let's look at the Matlab. We have created the subsystem for the signal. At the previous training video, we've created this system for simulating the signal. So this is the ramp, the constant, the linear increasing voltage. We raised it to the second power, multiplied by pi, and made it as an argument for the sine function. So if we simulate this, we can get this function. We can get this function x, cosine of pi times t squared over the interval from 0 to 1. So we've got our signal. As another subsystem, we simulated the system of basis functions. Again, the system of basis functions. It's like in our doc file, this system of basis functions is simulated here. So basically, again, we use integration to create all these functions. So we start from the constant, which is 1. After integrating 1, we get, well, this 1 as a constant goes to the output of the system. So this constant is the first function. It's actually t raised to the 0th power, which is 1. Now we integrate this 1 and we get linearly increasing voltage or linearly increasing function, which goes to the output. We integrate it twice. We integrate this linear function, we get parabolic function. We account for the gain because we understand that we need to account for this coefficient, which this power. So we use integration and account for these coefficients. We get all these 5, 1, 2, 3, 4, 5, with index running, index I running from 0 to 4. Basically, we've got 5 functions. We've got 5 functions. Now, let's try to simulate this. We simulate this, and the output goes to the CMOUT, to the workspace, to the working space. So we can take a look at these functions. We go to the working space. There are 2 output matrices, 2 output arrays, CMOUT. This is our output from our subsystem. Now we can plot it. Plot all columns. So we have 4 plots here and 5th plot here. This blue line at a level of 1. This is our 5th function. So with the interval, we can specify the interval, but basically it just numbers the 55 elements of this array. So, but this is the interval from 0 to 1 in terms of time. So 1, 2, 3, 4, 5 functions. These are our basis functions. Now we look at these equations. So we need to create subsystem, another subsystem for finding these elements, these W's, elements of the matrix, and these Q's, elements of this vector. Then we find the inverse of the matrix W, multiply it by Q, and we get the vector of coefficients representing these coefficients of this polynomial as a approximation or decomposition of our function by a polynomial. Let's take a look at this subsystem, or I already created this subsystem for you. So I open this analysis. So subsystem 1, this is our signal. So we used this signal as a subsystem. This subsystem can be found in Matlab in the Simulink library browser under ports and subsystems. There are different subsystems. For example, I can click on this subsystem, It's here. Now let's take a look at the blank subsystem. It's just input and output. It has only input and output. Now you can fill it in. You can remove this link and include elements, or you can delete this input and create a system which provides only output. So we delete it here. So we've created subsystem which outputs the signal X, Another subsystem. It outputs the system of 5 basis functions. So this is the output of this subsystem. Now these subsystems, this output signal from these two subsystems enter this another subsystem, which is the analysis. Let's look inside. Now it looks a little bit complicated, but if we take a closer look at these elements, basically it exactly follows these two equations. Here. So we have two branches. The first branch is for finding these W's, elements of the matrix W. The second branch is for finding these Q's. So in the first branch, where we obtain the elements of the matrix, we multiply the basis functions, all the basis functions by themselves. So we multiply every basis function by every other basis functions and integrate things. So let's take a look at this subsystem. We take all the output, the 5 elements, the 5 basis functions from the subsystem S. We transpose this vector, because this output comes as a vector column. By finding and transpose, we transform this vector column into the vector row. Now, vector row from here, vector column from here, and we use the matrix multiplication to obtain the matrix. So the first element, the first input, or the first element of this matrix product is the matrix column. So we multiply the matrix column let's illustrate this a little bit. So we get this matrix column. Example, we've got elements of matrix column 1, 2, 3, 4, and 5. Then we get the matrix row as a second element. 1, 2, 3, 4, and 5. We start multiplying. So as we multiply the matrix column by matrix row, by vector row, we multiply row by column. So as we multiply these two elements, we get W 1, 1. This is S 1, S sub 2, S sub 3, S sub 1 is here, S sub 2 is here, S sub 3 is here, S sub 4, S sub 5. I got it here. So these same elements are arranged in different order. They arrange in a row here. So S sub 1, S sub 2, and so forth. S sub 5. So as we multiply, we get these elements. W 1 2, W 1 3, so forth, W 2 1, and so forth. So we get all these W's. So all in all, we get this 5 by 5 matrix. There are other elements. We've got this 5 by 5 matrix. We've got this 5 by 5 matrix. And then we'll need to integrate these elements, because these are just the products. So, these are just the products. Now, we use the transpose matrix multiplication. So at the output of this matrix multiplication, we've got a matrix, the 5 by 5 matrix. Now we integrate this 5 by 5 matrix, and we get the W here, the matrix of the elements. We apply the general inverse to obtain this W raised to minus first power. So basically, we've got here the W minus raised to minus 1. Raised to minus 1. Now the second branch, we multiply the system of basis function by the signal. Now let's look at these matrix multiplications. It uses the matrix multiplication sign here, but we multiply element-wise here. Element-wise here. So we don't apply the matrix multiplication here. We multiply the X signal, single signal, by 5 functions, by 5 basis functions. We multiply element by element. So here we get the vector representing these 5 products. Single, the same signal, multiplied by 5 basis functions, and we apply integration to it. And we apply integration to it. So we integrate using this simple signature, this simple sign of, and this simple element, which is the integrator. So basically here at the integrator output, we've got this vector representing these Q's. These Q's. So at last we're ready to multiply. So we first introduce at the first input of the matrix multiplicator, we apply the W raised to minus 1, and at the second input we apply the Q. So this is the matrix, 5 by 5 matrix. This is the vector. One to 5 vector. So, and here we've got this input, X's, X capitals, which are the elements of the coefficients of representation of signal decomposition by the system of basis functions. Let's simulate this. So as we simulate it, now we see that the system recognized that S outputs 5 elements. So these multiple arrows represent the vector signals. So this is the vector. This is the single output, the scalar output, or scalar input to this multiplier. So here we've got these Q's. Here we've got this matrix, the inverse matrix, the W raised to the minus first power. So basically this subsystem works. This subsystem works. So this is it for this training video. and in the next training video we'll try to recover the signal from its decomposition by the system of basis functions. This system from the we recover the signal from its decomposition by system of basis functions. So until the next time, take care, guys.